Okay, let us take a look finally at a combination circuit and how do we actually analyze and do the math for this kind of situation. Remember Ohm's law, it's the center of everything that we're doing. The voltage equals the current times the resistance, V equals IR. And let's just take a quick look at our circuit here. First of all, we have a 60-volt power supply. We have one resistor here. Ooh, and then we have this weird kind of parallel circuit that's sitting right in the middle of there. Then we have another resistor here, and then we come back into the battery. Now, when you are looking at something like this, first of all, like always, write down what you know. So we're going to just take the numbers here. We're going to fill them in our chart below. This is our total voltage. So that is going to be 60 volts. Our resistance on resistor 1 is 5 ohms. Our resistance on resistors 2 and 3 is 8 ohms each. So 8 ohms. And our resistor number 4 has a resistance of 6 ohms. So we've got that filled in. Okay. That's everything that we know. Now, the way that you want to approach a combined circuit is you are going to have to use all of the circuit rules at some point. And so make sure when you're doing your work here, you have your handy dandy circuit rules somewhere on your phone, on the computer screen, written on an index card, printed out somewhere. We are going to use the series rules, and we're also going to use the parallel rules. The trick is figuring out when to use the series rules and when to use the parallel rules, and how to kind of play with that, okay? And the other thing that you're going to want to have on hand, because we are going to be doing some math, is you're going to want to have your handy dandy calculator right next to you. All right, now, after you have written down what you know, step 2. We are going to isolate the parallel part of the combination circuit. So what I'm going to do is I'm going to kind of draw some dashed lines around here. And what I want to do is I want to find a way to simplify what I know about this little parallel part of the circuit, so that instead of having 2 branches, I'm thinking of it as one element. And that means that immediately I'm going to need to come up with a combined equivalent resistance for those 2 branches. All right? And I'm going to call that REQ23. And let's see if we can figure out how to find that. And then once I kind of get this kind of simplified to kind of be like one element instead of a double branching element, then all I have is a series circuit. I have a series circuit with one element, a second element that I'm going to treat as 1 and not 2, and then a third element, and back it goes. So I'm going to have to use my parallel circuit rules anytime I'm working with this part of the circuit, and then the rest of the time I'm going to be using series circuit rules, and I'm going to consider this simplified element just another part of the series circuit. All right, so let's do the hard stuff up front, and it's not hard. So let's start by getting a combined resistance here, and this equivalent resistance 2, 3. Now, this is a parallel circuit, and that means we've got to use the circuit rules for resistance for parallel circuits. And that tells me that I get my equivalent resistance by calculating 1 divided by R2 plus 1 divided by R3, R2 and R3, and then inverting the whole thing. So each one of these has a resistance of 8 ohms. So my equivalent resistance is going to be 1/8 plus a 1/8 to the negative first power, or inverted, 1/8 is equal, I just know it's equal to 0.125. So the equivalent resistance here is going to be 0.125 plus 0.125 to the negative first. That's equal to 0.25 to the negative first, which is equal to 1 over 0.25, which is equal to 4 ohms. So my equivalent resistance for this entire part of the circuit is equal to 4 ohms. I'm just going to kind of put a box around that so it's kind of connected in and I remember that. Now, how does doing that help me? It actually helps me a lot because, take a look here. Remember that as long as I'm not inside dealing with this parallel part of the circuit, then I'm under series circuit rules. And so out here in the series circuit world, the resistance, the total resistance or equivalent resistance is simply equal to R1 plus this REQ23 plus R4. They just add together across the series, treating this whole thing as one little resistor. And so I can very quickly, because we're in series now, I can say that my total equivalent resistance is equal to R1 plus R equivalent to 3 plus R4, which is going to be equal to 5 ohms plus 4 ohms plus 6 ohms. And that is going to equal, oops, sorry, I'm moving around a lot. That's going to equal 15 ohms. And I can put that in here, 15 ohms. Okay, so now this is super nice because I can now calculate the total current because I have V and R for the whole circuit. So I'm going to use, remember I'm using my Ohm's law, V equals IR. I'm going to rewrite this to solve for I, the current. I'm going to divide both sides by R so that my I total is equal to my V total divided by my equivalent resistance for the whole circuit. And that's going to give me 60 volts divided by 15 ohms. So my total current is 4 amps. And then I'm going to write that in there. And I will come up here and I will write total of 4 amps right there. Now, remember, I'm out here in my series circuit rules. And so what that means is that each element of the circuit shares the same current. And so the current here at R1 is equal to 4 amps. And let's skip this for just a second, but here we know that R4 also has to have 4 amps. And we know that the current coming into the parallel part of the circuit, the current coming in is 4 amps, the current leaving is 4 amps. We don't immediately know what the current is across each of those branches of that parallel part of the circuit though. So we'll come back to that in just a minute. Now, let's think about where we are. Okay. We need to find the voltages and we need to find the current here. There's no immediate way to do that without the voltages. And so I'm going to kind of let that sit. But guess what? Look, I can calculate the voltage here at R4 and at R1. I can calculate those voltages quickly because I have 2 of the 3 components. I just use V equals IR. And so let's do that quickly. V equals IR here. So V1 is going to be equal to 5 amps. Or here, I'll do it in order, my bad. 4 amps times 5 ohms. So V1 is going to equal 20 volts. Okay? And now I can come over here to V4 and I can also do the same thing. So V4 is equal to IR. And so V4 is equal to 4 amps times 6 ohms. V4 is equal to 24 volts. Now, because we are still out here in the series circuit world, let's look at our circuit rules for series circuits and voltage. That tells us that the voltage of each component in the circuit has to add up to the total voltage. I know the total voltage. I know this voltage of resistor 1. I know resistor 4. I can get the voltage for this resistor 2,3 that is kind of my simplified pretend single resistor here. And that's what I'm going to do next. I'm going to get kind of a general voltage, okay? So I'm just going to come down here. Let me just draw a line so we're separated off a little bit. I know that the voltage total, and this is in our series again, is going to be equal to voltage of resistor 1 plus the voltage of resistor 2,3, that kind of combined simplified resistor, and plus the voltage of 4. This gives me, it's like third time I've done this video because it keeps freezing on me. 20 volts. V1, oh, my bad again. Guys, I'm sorry. I'm not redoing this video just because I'm losing it here. Okay, V total is 60 volts. 60 volts. Now we're back on track. V1 is 20 volts. We don't know the voltage of 2,3. And we do know 24 volts there. I'm just going to simplify algebraically now. 60 volts equals 44 volts plus V23. We're going to subtract 44 volts from both sides. And V23 is going to be equal to 16 volts. Okay, that's great. But I have two separate branches here. Well, here's the good news. Remember, when I actually go into this to look at what's happening, if I have 16 volts coming in, what is our voltage rule for parallel circuits? Every branch of the parallel circuit has the same voltage. So my voltage for R2 is going to be 16 volts. And my voltage for R3 will also be 16 volts. This is exciting because now, finally, I can calculate the individual currents across each of the parallel branches, and I just use Ohm's law. So here, I2 is going to be equal to the voltage 2 divided by R2, which is equal to 16 volts divided by 8 ohms. I2 equals 2 ohms. Watch what I'm about to do. I write ohms instead of amps for current. I don't know why. I just did it. I'm not going to do it again. Look, I'm just going to do it again in just a moment after I write some. Yeah, right there. I'm going to do it again. Ohms. That should be amps. Circuit. Make it amps on your paper and just pretend I didn't do that. Let's talk for just a moment about those Kirchhoff's rules. Those Kirchhoff's rules, the loop rule says that all of the voltages have to sum to 0. And I'm not going to go through that because it requires that you know which way is positive and negative, and right now I don't have time for that. This thing's going to break any second. But the big one is the junction rule. The current going in has to be the current coming out. And that current is going to get split somehow between all of the different branches. Now here, it's split equally because the resistances on each branch were the same. But let's take a look. If we have 4 amps coming in, it should split and then become 4 amps coming out. And if you look, we have 2 amps in each. 2 amps here, 2 amps here, means 4 amps coming out. So we are obeying Kirchhoff's junction rule here. And that, my friends, is an analysis. Notice that the most challenging part is not the little math bits, although it looks kind of impressive once you're all done with it. The most challenging part is thinking your way through, wait a minute, what can I do next? How do I think about this parallel piece as a single resistor? And then kind of going back and forth between looking at your series rules and then analyzing within that single parallel element, analyzing the branches. So every circuit problem is going to be different, and so this is an example of how to think through it. Work together though. It's supposed to be a struggle. It's supposed to be difficult. That's just proof that you are learning, and struggling and being confused. It's a good place to be, even though it's uncomfortable, because it means that you're stretching and you're growing and you're teaching your brain to think about situations and problems in new ways. Find people in class. Use your small groups. Work with each other. Make some friends. I know that's much harder now. We would be sitting at tables of 4 in the classroom. You would have a built-in group to work with. That's harder now, but it's more important than ever. Nobody does physics alone, and so I want you to find ways to get help from and offer help to other people. If this makes sense to you, just drop a message in somewhere in the Canvas discussions. Does anybody need help? Or put something in the chat that you get it, and if anyone needs help, to message you. If you're someone who this makes a lot of sense to, and this goes for everything we do all year long, offer to help, because it's hard for people to ask for help sometimes, and they don't know who to ask, and they don't always want to ask the teacher, although I'm always here and you can always message me. But we're all walking each other home. This is how you get home with a combination circuit.